Engulfment of nanoparticles by membranes is governed by a tug-of-war between adhesion, which wants the membrane to wrap the particle, and bending, which resists curvature. We'll visualize the three possible states, derive simple stability conditions, and see how spontaneous curvature tips the balance. Think of it like a tug-of-war. Adhesion pulls the membrane onto the particle surface, while bending rigidity pushes back against curvature. The key materials parameter here is the adhesion length. R sub W, the square root of 2 kappa divided by the magnitude of W, which sets the natural length scale for wrapping. A nanoparticle and a membrane can be in one of three states: free with no adhesion, partially engulfed, or completely engulfed with a closed neck. Let's put these side by side. The free state is stable if the local mean curvature m of the membrane segment in contact with the particle is greater than or equal to m sub f, r, defined as negative 1 over r sub p, a plus 1 over r sub w. When m drops below that threshold, but stays larger than negative 1 over r sub pa, adhesion starts and the membrane spreads, initiating partial engulfment. For the completely engulfed state, spontaneous curvature matters. Consider the unbound membrane segment, next to the neck with mean curvature m tilde. The closed neck opens if m tilde is less than m sub ce, which equals 2 times m plus 1 over r sub pa minus 1 over r sub w. Conversely, the neck is stable when m sub ce is less than or equal to m tilde, which is less than 1 over r sub pa. Notice these conditions depend on three material and geometric parameters: particle size r sub pa, adhesion length r sub w, and spontaneous curvature m. In fact, particle size and adhesion strength often appear via the contact mean curvature. M sub co equals 1 over r sub w minus 1 over r sub pa. Combining the stability of the free state and the closed neck gives four regimes: FST, free stable; CST, complete stable; BST, bistable with both free and complete stable; and PST, partial only. Let's map them conceptually. The local energy landscape reflects these regimes. In FST, the energy has a single minimum at free and a maximum at complete. In CST, it's the opposite. In BST, both free and complete are minima separated by a barrier. In PST, only the partial state is a minimum. Free and complete are maxima. For exocytic engulfment, where particles start on the inside and adhere to the inner leaflet, the same relations hold, but with all curvatures replaced by their negatives. M becomes negative m, m tilde becomes negative m tilde, and m becomes negative m. In the partial engulfment regime, the binding energy depends on local curvature. A membrane-bound particle feels an effective force along curvature gradients and undergoes biased diffusion towards specific regions, depending on whether it adheres to the outer or inner leaflet. Summary: engulfment outcomes follow simple thresholds comparing local curvature to material-controlled lengths. The free state is stabilized by sufficiently positive curvature. Complete engulfment requires a stable neck, influenced strongly by spontaneous curvature. Together they produce four regimes: predictable energy landscapes and curvature-guided motion under partial wrapping. These ideas unify drug delivery particles and viral budding under a common framework.